We are fortunate to have Mar for the last keynote lecture of the symposio. Mar is ICREA professor at the Instituto de Análisis Económico in Barcelona, and she's also affiliated with Northwestern University and is program director for climate and the environment of the CEPR and foreign editor of the Review of Economic Studies. Mar graduated from MIT in 2011, so she is fairly young for a keynote speaker at the symposio, which is just another marker of the excellence of her research trajectory. Recognition of this includes also, earlier on, the Banco de Sabadell Prize, and the Premio Nacional more recently, Clara Campeonor de Investigación. And she's also a fellow of the Econometric Society, and she has a an ERC consolidated grant. Mar is working at the intersection of industrial organization and energy economics with a focus on climate change and the energy transition. And she's going to talk today about successes and challenges of the energy transition. So thank you, Mar, and the floor is yours.
Yes. Well, thank you, everyone. I'm really sorry that I couldn't make it in person, but I got sick. Be careful. There are some viruses out there. But I'm happy that I can still connect online. I've never been to Mallorca, so I still will be shamed that I still haven't been in Mallorca. I thought 40 years old was the right time, but still, it seems like I will need to wait a bit longer. Today I will be presenting some of my research with the theme of challenges and successes in the energy transition. So this is a topic that it used to be a bit more niche, but nowadays everyone is familiar with what needs to be done. As you know, we need to decarbonize our economies, and a big part of it is by making everything electric. It's the part of the energy transition where we have seen the most progress, and where the goals are most ambitious, and where the goals tend to be more or less met, whereas in other sectors the goals are not being met. There is an ambition to have definitely carbon-free electricity by 2050 in many countries in the world, but many countries have targets at 2035 or 2040. And again, it's one of the few places where we have made some good progress in decarbonizing the economy. That said, it has come with some challenges, and one has been the fact that renewables are intermittent and we cannot always rely on them. So this has generated a lot of discussions on whether this transition is possible or not. There's also a huge need for complementary infrastructure. As we electrify everything, we will need more cables, more transformers, both at high and low voltage, and that also presents some coordination challenges and some investment needs that we need to pay. It's also true that electricity can become more vulnerable, the system, to climate shocks, and there are two ways in which the system is more vulnerable. One is that climate itself is affecting the weather, and the weather is a big part of what gives us electricity, like wind patterns, water availability, solar power. But also during climate shocks, demand can be very extreme because it's very hot or very cold and we have big demands of energy. So all of these things are putting pressure into the system, and still things we need to look up to and see how we can address these challenges. And then there are also growing pressures from other sectors. So unfortunately not in Spain, we are not electrifying our vehicles very quickly, but in many other parts of the world, electrical vehicles are being implemented quite quickly, and that's creating new demand for electricity. It does create opportunities, but also challenges. And a similar one is heating. As we electrify heating, cold days will be even harder to manage because a lot more of the heating will come from electricity, and that will put pressure in the grid. So these are all kind of challenges that we have. The electricity sector, as I told you, it's one of the places where we have made some progress, and actually it's one of the few places when it comes to climate change where we have some good news, because renewables are now quite inexpensive. They used to be very expensive or quite expensive, and therefore you needed a motivated government or a motivated policy regulator to put them in place. But nowadays, many of these resources, especially solar power, is cost effective even without subsidies. Here you see the trends for solar power, and you can see that it's only very recently in 2016, 2018, or 2021 in Canada that solar has become profitable. This is a huge deal because even in places like India, solar can be competitive against other technologies. And this is a big deal because these countries will continue to grow their energy needs, and it's great if we can grow them in a cleaner, more sustainable way. So as I mentioned, these are some of the successes, but there are also some challenges. Here you can see the amount of renewable energy in the world. It does contain hydro. And this is why Latin America is so good in here, because hydropower is renewable and it has a huge presence in Latin America. But in most countries, renewable powers are below 50%, as you can see. Europe is the one where we have seen the most progress, the most decided progress. But you can see that in many other regions, the presence of renewables is increasing. In the Middle East, as you can imagine, it's very, very low, but they do have a lot of solar potential. So we will see this also grow in Middle Eastern countries. So these are, again, highlighting a bit the successes of how fast the electricity sector is transforming, but also the challenges that we are still very far from 100%. So I will mention some challenges that remain. One is intermittency, as I was mentioning, that we have these resources that are not as easy to handle as a power plant. We have challenges in transmission and reliability, how to bring the right power to the right place at the right time. The problem of stranded assets. So what happens when there are stranded assets, and how do we get rid of them in a sense? Or how do we ease their exit from the market? There are also issues with acceptability and equity. So these changes are coming in very fast. As I was showing you in this graph, this is a huge change in percentage very quickly for any market. It's only in 10 years or 15 years, we have increased 25% points renewable generation in Europe. So this is putting pressure in different jobs, different types of energy forms, and therefore it can create challenges. And then there is a big one, it's the fiscal pressure of the energy transition, because nowadays there are huge climate impacts, and unfortunately we know that pretty well here. And with the climate impacts, we have a double need of adapting to climate as well as continuing this energy transition. It's what we call mitigation in climate terms. And therefore the energy transition, which is what we would call mitigation, will clash a little bit with adaptation, making sure that we have enough energy and enough resources to deal with the impacts of climate that are growing. Finally, there are a lot of tensions nowadays geopolitically, and one of them affects the energy transition regarding terms of trade. As you may know, there are a bunch of trade wars regarding solar panels, electric vehicles, and so forth. So it might affect quite a bit how we are doing this energy transition. So I think as economists, we can contribute quite a bit to understanding these questions and proposing maybe solutions with a diverse set of tools. So there are many different tools that we can use for answering each of these questions. Some of them are more big picture and maybe require more abstract tools. Some of them are very detailed, and we can get very detailed hourly data to analyze these issues. So I will basically tell you a little bit of my research and how I use different tools of economics to answer these questions, basically. So I call them tapas when I present outside of Spain. I know it sounds tacky presenting in Spain, but I call them 3 tapas. So I will present you 3 tapas from my research. One is a paper about Spain dealing with the issue of intermittency. One is a case study from Chile dealing with transmission. And one is a case study from the US dealing with stranded assets. I will present them hopefully relatively quickly. So the first one is the one for Spain, looking at the impact of intermittency in the Spanish electricity market, or to be precise, the Iberian electricity market, as it's quite integrated with Portugal. So this challenge that I put challenge number one is the issue that wind and solar are quite volatile and we cannot choose when they are available. Sure, we can store their power, but batteries are still limited. We are storing a lot of it, but we still don't have enough batteries to store all of it. So we need to deal with these changes, constant changes of wind and solar that happen in the market. This is just showing you the relative wind change in a matter of 12 hours or 24 hours, and it's in percentage terms. So basically wind in 12 hours can change easily 10, 20%, 25%. This is compared to the forecast. So it's quite uncertain. So in this paper, what we do, we look at what have been the impacts of wind generation in the last decade in the Spanish market. And basically, we do that via regression analysis. So it's a relatively simple paper with great data from Red Eléctrica, where we have hourly operational data from the market with prices, congestion costs. We pair it with emissions to look at the environmental benefits of wind. The nice thing about the data is that it has very detailed prices on the costs of intermittency. So when wind is intermittent, we have to pay for additional services in the grid. It's something pretty nerdy. Usually we don't look at it as economists, but in Red Eléctrica, we have very detailed data on that. So we wanted to look at how much do the results change on the benefits and costs of wind when we take into account these more nerdy services that need to be provided and can be complicated by wind. We find that even taking into account these additional costs, consumers are better off with wind. And this was surprising to us, maybe not the overall assessment, because we do need to decarbonize the market and therefore the benefits from wind are very large. But in our findings, we find that these intermittency costs not only don't revert the answer, they are also quite small quantitatively. So there are many studies in economics that look at the benefits of wind, and typically they have been measuring the benefits in terms of emissions or the impacts on prices. So again, what our contribution was with this paper was to look at more especially the cost of intermittency, balancing cost, reliability, frequency, services, and all of these things. So the data is very detailed, as I mentioned, mostly from Red Eléctrica, although also from OMIE, which is the market operator. And we basically do, again, a very simple cost-benefit analysis with hourly data from this market, quantifying the impact of wind. We focus on wind because during this time period, wind was much more present than solar, although lately solar power is the one that has been growing the most in Spain. So the identification strategy, again, it's very simple because wind is very volatile, so it does provide a lot of random variation. I tell my students when we look at regressions that it's the perfect X variable, it's truly a random variable, and therefore we can regress it on an outcome of interest and get a pretty clean estimate of the impact of wind on a certain outcome. There are some details on how we want to think about it. Do we want to use forecasted wind, actual wind, or do we want to instrument it with wind speed? But at the end of the day, the answers are quite similar no matter what the econometric approach is, so it's easiest to explain as a simple regression. We allow for the effect to be different depending on whether there is a little bit of wind or a lot of wind, and that will give us the marginal effect at different levels of wind. So as I mentioned, we focus on these additional costs, not the impact on prices or the impact of emissions. We do that for the overall cost benefit, but for the main part of the paper, we focus on operational costs, which are these additional costs from having wind. And we see how much these costs have increased because of wind power. So you can see here the average impact on the costs, as well as the marginal impact on the cost. You can see that this is increasing and that the marginal impact is positive. This is what we were expecting because wind makes dealing with the market harder. So the key question for us was how big this is. And you can see that the marginal effect of wind is between 0.1 and 0.3 euros. This is in euros per megawatt hours. And even if you don't know about electricity, I can tell you very confidently this is a very small number. So what we are saying is that if we put 1 gigawatt of wind in the grid, which is quite a bit, 1 gigawatt is one nuclear power plant, the costs only go up by 0.2 cents. Nowadays, the cost of electricity are around 100. So 0.2 is a very, very small amount. So I guess the conclusion of our first part of the paper is that the costs go up, but really much less than we might have expected. Importantly, we don't see this cost blowing up when there is a lot of wind, which is something that surprised to us because typically even engineers would have expected this effect to grow exponentially. And instead, we found an inverse U shape. So to investigate this, I'm an IO economist at heart, so we got a lot of bidding data from the power plants. And what we found out is that when there is a lot of wind, many power plants are available and don't have much to do. So they compete more fiercely to provide these services, lowering the costs. We decompose among different costs. I don't think we need to go into it, and even less with an online presentation, but mostly we just looked at what's happening in the market and what are the different costs that go up and down to double check if this made sense. The more interesting part of the paper, even if it's the less well identified part of the paper, is that we try to discuss why the costs have been so small. Engineers had been expecting these costs to be higher. And what we highlight in the paper is that on top of technological innovation, there has also been a lot of market innovation that has gone with the incorporation of renewables into the grid. So we see in many, many markets with a high degree of renewables, like California, Germany, or Europe more generally, that there have been modifications to how the market works so that the market is more efficient and it can integrate renewables better. Maybe the most exciting case of market innovation is California, who convinced all the neighboring states in the west of the US to join a balancing market so that they could integrate renewables in a cheaper, more efficient way. For your context, I will talk later about regulated markets. Most of the neighboring markets that neighbor California don't even have a market. And they agreed to join a market with California for the last minute imbalances so that they could lower the costs. So this is kind of a huge market innovation. Germany quickly moved into half-hourly markets. They had hourly markets and they realized with renewables you needed faster trading, so they also innovated there. In Spain, there have been many innovations to try to deal with renewables, and in the paper we highlight one, which was improving the way in which wind farms participate in the market. I had done some previous work, and Natalia also has some previous work showing that the design before 2014 led to some funny incentives by wind farms that made them overbid, bid too much wind into the market. It led to many zero prices that then had to be reshuffled in congestion markets. So it basically required a lot of doing and undoing. And there was a change that basically avoided the zero prices. You can see the blue is the before, and it moved the market to something that was clearing more to the expected price and was avoiding a lot of this balancing that was very costly. And what we see indeed is that after this change, we see a drop in the cost of balancing services. In the paper, we highlight this change because it's one of the easiest to quantify, but there have been several other changes in Spain that have enabled the reduction in costs. And one is, for example, that they now allow wind farms to participate in balancing markets. So wind farms used to be seen as a problem, but nowadays they can participate in some of these balancing markets. In particular, a wind farm cannot pretend it's more windy, but it can pretend it is less windy. So they can participate in some of these services depending on the direction, and that has improved the outcomes in the market as well. So just to give you some examples. So the paper is a bit longer and we do a full cost benefit. What we show in the paper is that the overall cost benefit is positive, although it depends on what you want to assume about the benefits from reduced carbon emissions. I think wind farms were perceived as a costly mistake because Spain invested very early in the technology, like Germany, so they paid a higher price than other countries. But even at those higher costs, it's still justified, given that the social cost of carbon is very high and it keeps increasing. Now, the results for intermittency are quite positive. There seems to be less cost than we thought, and the overall cost benefit is not impacted heavily by the incorporation of these considerations. However, I have to say that going forward, this still remains a bit of a challenge, especially for many, many days without wind, many, many days without solar. These are situations in which we still don't know how we will deal with them. But at least it means that for the early stages of the energy transition and the middle stages of the energy transition, like Spain or Germany would be at, this doesn't seem to be a huge challenge. So this was my first TAPA. The questions maybe at the end, or how do you want to do it, Pedro? Because if anyone has one question about this TAPA, I could also answer it now. I will continue because I don't hear. Oh. Okay, perfect. Yes. Great. So I had another example where I will show you a different set of tools to analyze a related but different question, and it's going to Chile. It's looking at transmission expansion, and it's basically a study to see what are the costs and benefits. Very similar in some ways. It's a cost-benefit analysis of expanding transmission. So the challenge is that oftentimes we have renewables in the middle of nowhere. That's where the best resources are. But the grid was not built to bring power to the middle of nowhere. So we have this need of building transmission lines in places where before there was not much of a reason to have them there. In the case study today, it will be the Atacama Desert, which is virtually empty. So there was barely any infrastructure, and now they are building large infrastructure to bring renewables into the cities. This might be the case of Atacama, but it's very common in other places. So in China, for example, they have built huge transmission lines to build wind from the west to the east of China, which is more populated. In Texas, they already had a transmission line in 2013 to bring wind from the west of Texas to the east, which is more populated. So there are many, many examples of transmission projects that are needed to allow for harvesting renewable power in remote areas. The case that we study with Luis and Koichiro is the case of Chile, which has some nice event studies because they built two big lines in 2017 and 2019. So this is kind of the first event study, and this is the second event study. In one case, they connected the north of Chile to the center, and in the other case, they improved the connection between the center, the north center, Atacama, with Santiago. So the goal of the paper is to look at the before and after of building these lines to understand their benefits. And initially, our paper was supposed to be an event study because we have very highly detailed data on the electricity market, hours before the transmission line goes on and hours after. So you can imagine doing a very, very sharp event study around these transmission line projects. However, very quickly we realized that we would be missing quite a bit by just doing an event study, because on top of the transmission line, this transmission line has triggered a lot of investment in solar power in Atacama. It's kind of one of the main benefits. And when we do an event study, we would miss the investment benefits because they don't tend to happen exactly at the same time. So in the paper, we derive a framework to think about the event study and how investment effects can contaminate the event study. And then we propose a structural model to get at the full effect. So with the event study, we get at the immediate effects of building the line, but with the structural model, we can do capture better the overall impact. The Atacama, as I mentioned, is one of the places in the world with the best solar power, not only because it's well located, but also because it has no clouds. And I'm sure some astronomer aficionados in the room know that. So in Chile, which has been traditionally very dependent on fossil fuel from other countries, and from Argentina, for example, which has not always been reliable, they benefit a lot from this available and cheap power in the desert. So they made transmission projects. They actually have several more going on to better connect the country and bring this cheap power to the city. So the summary of our paper, the more general interest theoretical part or conceptual part, is to highlight how the event study might miss the investment effects. So we show this in the paper in more detail if you are interested, but we look at a very simple trade model with two regions, A and B. We imagine them as being in autarky and then opening to trade. And what we highlight is that if they open to trade without investment effects, we would find the typical gains from trade. But if opening to trade leads to investment, then we will have a shifted curve, and therefore we will have additional effects. Now, the main point of the theoretical framework is to highlight that if we do an event study between autarky and trade, we might get biased results, in a sense, from the overall effect of the expansion. One, because we might be comparing this point, the autarky point, to when investment has already happened. But we would be thinking this is just the transmission line effect. So in that case, we would be getting an overstatement on the gains from trade, but we would be missing out on all the investment that has been enabled by the expansion. So in the paper, we discuss these different formulas and how to think about it, but ultimately the paper is empirical. So what we do is do an event study first, and then create a structural model that allows us to compute these solar investment benefits. So let me show you the empirical part. In the empirical part, we first do the event study. Very simple, it's a regression where we regress the costs of producing electricity in Chile. And we have two dummies, the first line and the second line. We call them the interconnection and the reinforcement, and then a bunch of controls. Maybe the only thing that's not a standard from other event studies is that we have a control that's a synthetic control. It's the cost of electricity as predicted by a model, a very simple model. The reason for having this control is that hourly electricity costs are very volatile, so it's very difficult to create a good control with linear versions or quadratic versions of the cost of gas, the cost of coal. So this is a very nonlinear control that predicts very well the movements in C, so that we can get a cleaner estimate from this event study. And the interest is to get alpha 1 and alpha 2. This is a bit like the previous paper. We already knew that alpha 1 and alpha 2 should lower the cost of electricity. This is a clear case where there are gains from trade. The question is more by how much. And what we find is that after the interconnection, the costs of electricity decrease in about $2 per megawatt hour. And after the reinforcement, they decrease a bit more, but not as much. In total, the cost decreases depending whether we look at the hours with the most sun or other hours. The reduction in costs is about $2 to $3 per megawatt hour, which given the average costs during the period, it's a sizable amount, between 5 to 10% reduction in costs. So we could finish here and compare these to the cost of the lines and get a cost benefit. However, I guess we didn't stop there, and we decided to look into the issue of investment because we were a bit worried that these numbers were a bit biased by the fact that a lot of solar power was already waiting in Atacama for the line to connect. And indeed, this is what happened. The line was announced in 2014, together with a lot of ambitious targets for renewable power. So there were already many solar panels going into Atacama. These solar panels going into Atacama, the red line, they were getting zero prices, the dark green line at the bottom. So they were waiting for prices to go up for about 1 or 2 years, and then the transmission line came in. So it's hard to imagine that those solar panels would have occurred if they had not expected the transmission line to take place. And that's what we will try to do with a model. We try to compute how much of this red line is thanks to the transmission line. So to build a model, it's a pretty parsimonious structural model of the electricity market in Chile. We basically construct a model of the supply of Chile. The demand side is very boring. We just take it as given. We built a model with 11 zones for Chile. And then we basically construct the supply and the demand curve in each of these zones. And then we allow for trade up to the transmission constraints. And we will basically compare a world where there is better trade and a world where there is less trade and see how well it fits the model, the data, and so on and so forth. So it took a lot of time to do that, but I just give you here a bit of the ingredients that go into this. The network model, actually, we made it into 11 zones, not 5. Supply curve, demand, solar potential, and the cost of solar. So then we just bring it into the model. Oh, and the other thing I should say is that for each of the combinations of transmission, we will endogenously compute the optimal solar investment to get at how much or how less solar there is with and without transmission. I see I simplified the slide a lot, so I don't have those equations here. At the end of the day, we do the cost benefit and we compare the benefits that we compute from having the transmission line to the cost, which was 1.8 billion, more or less. And we look at the changes in consumer surplus, the changes in net solar revenue, so the profits that the solar panels made, and the changes in environmental externalities. And overall, what we find is the transmission line was a good investment. However, we find that the cost benefit changes quite a bit if we take into account the investment benefits versus if we don't take them into account. If we don't take them into account, the transmission line is probably still profitable, but it takes about, depending on the discount rate, it takes 50 years. So it's a very long time horizon. Whereas if we do the full cost benefit with the investment effects, we find that the line pays itself very quickly in a matter of 6 to 8 years. And given that these are very long-lived investments, it's very clear that this should be a no-brainer in a sense. So even though you could come up with a positive assessment under both, it's much easier to justify the investment and find a cost benefit that's positive if we do the harder cost benefit, including investment effects. So this case for Chile was a very easy one in a sense, because it's very clear that there are massive benefits to Chile from solar power in Atacama. It's really a good source of power, and Chile otherwise has very bad energy resources. Additionally, the political economy in Chile makes the expansion very easy because it's taking power from a region that doesn't have many people at all to other areas of the country. So it was relatively easy to do these projects. In Europe, for example, the situation is very different, and I think it will make for very interesting research going forward. For example, a big debate in Europe now is what to do with solar power in Spain, which is way better than anywhere else in Europe, maybe Italy and Greece a little bit, but there is a lot of land in Spain that's also relatively empty. And there is a bit of a challenge on, will Spain attract manufacturing, or will Spain send cheap power to the rest of Europe? How are we going to do these lines? Who's going to pay them? Where are they going to go? Because as you may know, these are not easy to justify projects. And for example, in the Basque Country, there are already some challenges there, even though it's set to be expanded in a few years. So these, I think, would be very interesting questions for anybody interested in trade, political economy, and definitely energy. Awesome. So I'll go for my last TAPA. This TAPA is a bit uncooked because it's still work in progress. It's a case study looking at the case of stranded assets in the US. I do think stranded assets is a huge question for anyone interested in the energy transition. This is a first attempt at looking at it, although it's looking at a bit of a particular issue, not the full big picture. So stranded assets, it's no surprise, should make the transition harder. First, because they do change the cost-benefit assessment. If they are already there, we might well use them a bit more. But also because they create a lot of incentives to not make them go away. In the US, stranded assets take the form of coal power plants, and soon will be natural gas power plants. It's very hard to kind of phase them out for many reasons. One is that in the US, there is no carbon pricing, so coal is still relatively cheap. But second, it's that it has a lot of jobs related to coal, not just in power plants, but also in mining. So it's been a huge deal in many legislation discussions, and oftentimes legislations get turned down for that reason. In our paper, we look at a particular issue, which is the issue of regulation, that some of these coal power plants, quite a few of them, are heavily regulated. And we try to see whether the regulatory incentives of these coal power plants could be distorting their behavior. This is based on some previous discussion by the Union of Concerned Scientists saying, why are we using coal power plants if they are no longer cheap? And why do we still use them? And again, the context is the US, where coal power plants are still regulated. In Europe, most of the coal power plants are not regulated. In Spain, some of them were regulated or were receiving subsidies to run, but it's been a while that coal has been mostly phased out in Spain, not in other parts. In the US, again, coal is being used less and less, and some of the coal power plants are exiting, but there are still quite a few quite old coal power plants that are being used a lot, and in a way that's hard to justify. So the question of our paper was to see, can the regulatory structure be contributing to this delayed exit by coal power plants? This is a harder question. It's also not as well identified. So the tools we use is descriptive evidence and a structural model of regulation. So compared to the Chile project, in the Chile project, the structural model is very faithful to how the world works. It's about power lines and power plants. In this paper, we also have a faithful model of how the electricity market works. But then on top of that, we put a much more stylized model of regulation. And this one is a much more kind of theoretical model of regulation that we will try to identify with the data. So what are some of the findings we have? We highlight that the incentives to use existing capital are distorted, and that these coal power plants are indeed being used even when it's not profitable. We think that this is important for this coal to gas transition, which is delayed, but also for the next gas to renewables transition. Because again, if the incentives are to keep using these plants, even if they are not profitable, then it will take much longer to stop using them. The motivation evidence, you could see a little picture before. I put here the bigger one. Motivating evidence for us, and this is totally not identified, it's purely descriptive. It's basically comparing whether regulated plants are exiting the market versus restructured plants, the ones that are privatized. And what we see is that in the market, the regulated power plants are exiting at a slower rate than the restructured ones. Take these again as suggestive evidence, but not full evidence. So what we will do is build a model of a regulator who is regulating the plants that are in the green line, the regulated plants, and it's trying to make them behave as optimally as possible, but considering that we are in a regulatory setting. So it will be paying them their variable costs, but it will offer some carrots so that they are as efficient as possible. And what we put in the model is this idea of being used and useful, that the regulator will put some carrots if the power plants are used more. In practice, the way we interpret this is that if a coal power plant is never used, then it might be harder for the coal power plant to get some upgrade or to get some new filters, and eventually it might be replaced earlier. So the regulated plants might have an incentive to keep using them so that they keep getting upgrades. The utility will optimize and try to choose what to do with their power plants, whether to retire coal or whether to build more power plants, and hourly, they will just choose how to generate. And the incentives, again, there are these conflicts that they want to operate as efficiently as possible because they will get some rewards from this, but they also want to use their coal power plants so that they can prove that they are useful. The empirical approach is basically estimating a model, an hourly model, which is quite well identified, but then the dynamic model and the regulatory model, which is a bit more, structurally identified. And we will do that with a nested GMM approach, very structural, so a nested fixed point approach, where we solve the hourly model, we solve the investment model, and we estimate the dynamic and regulatory parameters that fit the model best. So the nice source of identification, we do have some identification. The nice source of identification in our model that's helping us identify the parameters is that natural gas used to be expensive, but nowadays is quite cheap. So there are very strong predictions in the data of how much we should be using coal or gas before natural gas was cheap and after natural gas is cheap. And that's in a sense the variation that's helping us identify the model. So let me show you a little bit the empirical support for this. So what we do is basically look at how often do coal power plants run their generators, even though it seems it should be cheaper to do it in some other ways. To be clear, there are many reasons why a coal power plant might be used, even though it seems they shouldn't. There are many reasons, but basically we try to see if the regulated coal power plants do it more often than the non-regulated ones. So here I put the extra probability that a natural gas plant runs when their cost is higher than the price, and obviously it should be negative. Gas power plants are less likely to run when their cost is higher than the price. And this is the probability that coal runs when their cost is higher than the price. And it should also be negative. But you can notice that there are some power plants where for coal, this is really not that negative. And you can see them in green. And for the red ones, you can see that they are much less likely to run when the cost of coal is higher than the price. So the green ones are the regulated ones, and the red ones are the non-regulated ones. So from this, we basically sort them here so that it's easier to see. You can see here the utilities that are non-regulated and the utilities that are regulated, and you can see that utilities that are not regulated are very unlikely to run when their cost is higher than the price. This is what economic theory would predict. But in the case of regulated power plants, that's actually not that's true. Obviously, they are a bit less likely to run, but it's much less than in the other markets. So this is, again, the motivating evidence that we use to then estimate the model. I will not go over the structural model. Again, it's an hourly model nested into an investment model. And maybe the more interesting part is that in the profit function, we have some regulatory parameters, some carrots and sticks that the regulator is providing to the companies to operate their power plants. We get the hourly models. These are the hourly model parameters. These are very well identified. These are very well identified. These are also decently identified. The ones that are maybe more structurally estimated is this one. This is a regulatory parameter penalizing the companies if they are too expensive. And this is the parameters for the used and useful that are rewarding the companies if they keep using their coal power plants implicitly. And then we use these parameters again and the model to do a bunch of counterfactuals. I will not go over the counterfactuals in too much detail. This is work in progress. So we are recooking our TAPA as part of a revision. But our results are basically that these regulatory parameters do delay the exit of coal substantially. We find that if we try to optimize at the margin these regulatory parameters, we still see coal capacity being present and delayed. So our results are a bit negative in the sense that it's hard to go around the regulation. We do find that putting a carbon tax helps a bit, but there are still some remaining problems. The current rate of return regulation basically leads to half of coal power plants still being there compared to the optimal. Going forward, I think this is a big topic for anyone interested in these issues. Stranded assets are a big deal, not just in power. And I think for the case of Spain, our biggest stranded asset is the car sector and how to deal with the transition in the car manufacturing sector. And I don't think it's a coincidence that the electric car is taking such a long time to take place in Europe generally, but even more in Spain. So these are difficult issues with a lot of winners and losers, and they don't have easy answers. So I do think we need way more, many people and economists too, working on these topics. So as conclusion, I hope I provided you with some appetite for the full dish on these three tapas. These are different papers with very different tools looking at the impacts of the energy transition in different areas and different topics. But there's a lot of work to be done. And as Pedro said, I have an ERC project in Barcelona. We are very friendly and we get visitors all the time. So feel free to come to Barcelona.
thanks a lot, Mar, for a very, very nice talk, and thanks for delivering in spite of the flu. So we have time for questions. Now, if we use the microphone, Mar may be able to hear us. We will try, and if it doesn't work, I will repeat the questions. Any questions?
Hi, Mar, thank you so much for a great talk. Miguel Almunia. Can you hear me? Can you hear Mar?
No, no.
Okay. So I have a question. You mentioned that Spain has this opportunity to have a lot of solar energy to produce electricity, and there might be a surplus. And one of the ways in which we can make that surplus into something useful could be this green hydrogen that we can produce and then either use it to produce things here or to send them elsewhere to Germany or something. So what do we know from this area of research about the potential of that strategy for Spain, and what are the factors that might determine whether we use these new energies here as opposed to exporting them elsewhere? Thank you.
So, Mark, you hear me? Yeah. So you didn't hear the question, right? Okay, so Miguel was asking about the use of green energy in Spain, about the opportunities for that, what you think is the potential, and what you think are the factors that determine whether the energy that is produced is used here or is exported.
Yeah, very good question. I think the potential is very good. Like I often tell when I talk to policymakers that the location on Earth is not delocalizable. So you can, there's a race to the bottom on labor cost, there's a race to the bottom on environmental regulation, but you cannot do a race to the bottom on where on Earth you are located. And Spain is quite well located in the context of Europe. So it has a lot of potential. The tricky thing is, yes, how to bring that power where industry is, or whether this will be an attraction to industry. And I think data centers, for example, now are showing interest being in Spain. Spain is also very hot, so I don't know the math for that, but it seems to me there are many other electric-intensive industries that might want to locate here. I don't know if they will come with many jobs or not. For example, data centers, I'm not sure they come with many jobs. I have no idea. But it is a very interesting discussion. I don't have enough detail to tell you what I think will happen. I think it will be a mix. The UK, for example, was thinking about running a line underwater. And interestingly, it was thinking about running it from the UK to Morocco rather than to the Peninsula Iberica or some other place. So I think there will be interesting choices made. But I don't have more than that. But I want to look more into it going forward. I think we need to build a model of winners and losers from these different transmission lines and from the location of industry, and I don't think we have such a model yet. Yes.
Questions?
Hi, I will make it short so it's easy to translate. I was wondering, in this transition towards more renewable energies, what the role of nuclear energy is, and I'm asking especially because, like in Italy, there is a big discussion about opening new nuclear plants, and I was wondering if there are like complementarities or substitutions between these two sources of energy, let's say renewables and nuclear. Thank you very much, and thank you for the talk.
The question is about the role of nuclear in the transition towards renewables in general. In particular, the question refers to Italy too, where there's a big debate about whether to install new nuclear. So it's a question, what is your view about that, and are there any complementarities
Yeah, I think the big question is whether it will be more like batteries and renewables versus nuclear and renewables, and how much of each. For nuclear power in Europe, it has been very late and very expensive, except for obviously France. So I don't know. I'm a bit not. I don't think it will play a big role. I think because again, every power plant has come in very, very late and very, very expensive. However, now with artificial intelligence, the big companies are putting a lot of money into nuclear. It's coming expensive, but they are trying to develop it. So there might be some surprise in there. My worry about nuclear plants, the traditional kind, is that they cannot operate under extreme conditions. And in France, for example, in 2022, they underperformed because it was too hot and the rivers had river water was too hot and there was too little water. So I think in places like Spain and the south of France, Italy, nuclear will be a risky technology in the sense that it could be not available when you need it the most. And it has happened before already, but again, this is a bit hard to predict. But in Europe, I would say it will be too expensive and we can do cheaper with batteries and renewables, but I don't know. I think some of the nuclear plants we have will still go running, but maybe not new ones because it would take a very, very long time and time is kind of essence.
Questions? Okay, so there's no other questions. Thanks a lot again, Mar,
Thank you for the patience to have a webinar in beautiful Mallorca. So yes.
thank you.
Yes, thank you. Muchas gracias, ¿eh? Hasta luego. Gracias, lo siento, ¿eh? Gracias. Sí.